afternoon also from my side. My name is Riccardo Battisti. I work for the Italian company Ambiente Italia, and I also coordinate the EU-supported Smart Reflex project. And this webinar was organized also thanks to the activities we are doing in this project. Let me first of all thank the European Copper Institute for hosting this webinar, and the information portal solarthermalworld.org for the promotion of the webinar, and of course, as Fernando was saying, also for making the recording of this webinar available afterwards. Let me also thank the speakers, of course, our Smart Reflex partners who are working with us in the project, and of course, all of you who gathered this afternoon. So I will be very brief in introducing the topic of today. You know that this webinar is focusing on solar thermal for district heating. Our Smart Reflex project has a wider scope than that because it is about the use of any renewable energy source for district heating and cooling. We are basically collecting the experience from 6 different regions in 4 European countries, as you can see in this map. And we tried to really set up a comprehensive approach for developing 100% renewable district heating and cooling in these regions by doing different kind of activities. First of all, a regional task force set up with all key stakeholders, also involving the regional authorities. Then very comprehensive capacity buildings, workshops, and activities in all of the participating countries, and also a very strong connection with some coaching countries, let's say, from the point of view of renewable district heating, which are basically Denmark and Germany in this project. As you see, again, also the technological scope is very large, and it will involve all the renewable energy sources, but also industrial surplus heat, low temperature networks, and also all the topics concerning, let's say, the city planning and also the building retrofitting. I just want to give you an example of some of the results we developed within the project and of the tools we are making available to everybody, to the public, through our website. So we developed a guide for regional authorities willing to go towards 100% renewable district heating and cooling, and also some recommendations for setting up a task force on the same topic at regional level. Each of our regions developed a regional strategy, so including a practical action plan for developing, for fostering the development of district heating and cooling. We also have the training material available from this capacity building workshop, which we used to train more than 500 people in the project. And we also developed, and we are still developing because we are in the final phase of the project, about 20 case studies, feasibility studies on real plants at local level, and or some case studies about effective policies for REST DHC development. So you will find all this information and many other interesting tools on our website, on the website of the project, which is smartreflex.eu. So I think that's all from my side. So now we can start really with the technical presentations. We will have 3 presentations today, and we will start from a very hot topic, I could say, because you know that solar thermal, of course, has a production curve which has its maximum during the summer, and this surplus heat which can be produced by solar during the summer could be a very interesting input for district heating grids if the district heating grid is also equipped with a seasonal heat store. So to store the surplus heat produced by the solar thermal plant during the summer and use it then during the winter season. The first presentation will be given by Thomas Schmidt. Thomas is a member of the management at German Research Institute Solites, and Solites has been working really with a long-term experience on seasonal heat storage, both in Germany and Denmark. And so Thomas will report about some real monitoring results and performance from some examples of this seasonal heat storage. So Thomas, the floor is yours.
Yes, thank you very much, Ricardo, for the introduction and also for the opportunity to give this presentation today. Welcome to everybody. As Ricardo already announced, my presentation is about monitoring results of seasonal heat storages. I will start with a short introduction. After this, I'm going to present two projects to you. The first one is a solar district heating system with a pit thermal energy storage in Dronninglund in the north of Denmark. And the second one is also a solar district heating system, but with a borehole thermal energy storage that is located in Kreilsheim. It's a little city in the south of Germany. And at the end, there will be a short summary. So starting with the introduction. This slide shows 4 storage concepts that have been developed in the last decades for large-scale seasonal heat storage. So if we start from the upper left side, we have ground-buried tanks. On the upper right side, the pit thermal energy storage, and on the bottom we can see 2 concepts for so-called underground thermal energy storage, so the borehole and the aquifer storages. If we look at the upper 2 concepts, they are characterized by a wall construction that clearly separates the storage volume from the surrounding ground. So in case of the tank storage, we have a static construction in the sizes we are talking about. So starting from some 1,000 cubic meters of storage volume, we normally have concrete constructions. On the upper left side, the pit storages, they don't use a static construction, but it's just a kind of a wall, of a plastic liner wall construction separating the storage volume from the surrounding ground. The plastic liner can be supported by an insulation layer, but not necessarily. For the underground concepts, we can see already from the pictures that there is no clearly defined storage volume. We just have different devices for charging and discharging the ground with heat. And in the case of the borehole storage, we have the borehole heat exchangers that are used for heat transfer to the ground and from the ground. And the heat transfer inside the storage volume then takes place mainly based on conduction. It's a so-called closed system because of the closed borehole heat exchangers. The aquifer storage is an open system, so for bringing the heat into the ground or extracting it from the ground, groundwater is extracted from the ground layers and is heated up or cooled down by the system on top, and afterwards re-injected into the ground. So the following 2 projects I will present you is, as mentioned before, the first one with a pit thermal energy storage and the second one with a borehole thermal energy storage. So on this slide you can see an air view of the solar system in Dronninglund in Denmark. We can see in the center the main heat source is the large solar collector field with almost 38,000 square meters of solar collectors. A little bit more in the back on the left we see the cover of the pit thermal energy storage with a volume of 63,000 cubic meters. This solar system is then connected by district heating pipes to the main district heating plant. In the district heating plant, we can see this table on the upper right side. There are some more energy producers like a heat pump, a CHP unit, some boilers, and yes, the entire heat demand of the district heating network is about 40,000 megawatt hours a year. Here you can see some pictures from the construction phase of the pit storage. On the upper left side, you can see the situation at the end of the groundworks. So the pit is realized and the walls are prepared for the installation of the liner. On the upper right side, you can see the plastic liner after installation. So the plastic liner at the bottom and at the side walls. It's an HDPE liner. On both pictures, you can see in the center of this tower. These are the charging and discharging devices. So there are possibilities on 3 levels to extract and inject water. The lower left side shows the storage after filling with the water. And on the lower right side, you can see the cover construction, kind of a vertical section. So starting on the water surface with another HDPE liner that is floating on the water surface, followed by some supporting layers like some mesh grids and fleece, protecting fleece layers, and then followed by 3 layers of insulation material that are then covered and protected by another plastic liner to the surface. So coming to some monitoring results, we can see on this graph the monthly heat balance for a 2 years period for the years 2014 and 2015. The orange bars show the monthly heat demand that is, or the monthly heat that has been charged to the storage, and the green bars show the monthly heat that has been discharged from the storage. The black dashed line shows the energy content development inside the storage volume. So if we look at the orange bars, we can see a seasonal development. The main charging during the summer period and hardly any charging during the winter period. If we look at the green bars, at the discharging development, we can also see a seasonal development, but it's not so clearly separated as for the charging. So we can also, during the summer period, we can see large amounts of discharging. So this shows us that the storage is not only used for seasonal storage, but also in parallel for short-term storage. Here we can see the temperature development in the same period, so 2014 and 2015. The colored lines show temperatures on different height levels inside the storage. So the black and the red and orange lines show temperatures more on the top of the storage, and the blue lines show the temperatures at the bottom of the storage. We can see at the beginning of 2014, the start situation was more or less 1450 degrees of temperature in the entire storage. After the charging period, until the summer, we reached maximum temperatures of some 85, almost 90 degrees on the top of the storage. At the bottom, at that period or at that time, we have temperatures between 50 and 70 degrees. From something around October, the discharging period starts. Can you see this pointer? I don't think it works really good. So around October, the discharging period starts and ends somewhere in February in the following year. Somewhere in the middle of the discharging period, you can see a kind of a step function. This is somewhere beginning of November. At this time, the temperature level on top of the storage was not high enough anymore to be used directly in the district heating network. So at this time, the heat pump started operating and was cooling down the storage volume further down to a temperature level of 15 degrees at the bottom of the storage and about 20-25 degrees at the top layers at the end of the heating period 2014-2015. And a similar development can be seen for the year 2015. If we look at the yearly figures of the storage, so we can see here the the main energy flows of the storage. So we have, in the entire year 2015, we had almost 13 gigawatt hours of heat that were charged into the storage, and a little less than 12 gigawatt hours that were discharged from the storage. And from the heat balance, we can calculate the thermal losses of the storage to a little bit more than 1 gigawatt hour, so the 1275 megawatt hours for the year 2015. From these yearly numbers, we can calculate some characteristic figures that you can see on the upper part. For example, the storage efficiency. This is defined as the amount of heat that was discharged from the storage referred to the amount of heat that was charged to the storage. We can also calculate the so-called number of storage cycles to 2.2. This is an indicator for the amount for the heat turnover of the storage. So it is defined as the amount of heat that was discharged from the storage referred to the heat capacity of the storage. And with the heat capacity or with the given temperatures, we can calculate the heat capacity of the storage to some 5,500 megawatt hours. So far to the first example. I will now move to the second project, the borehole storage project in Kreisheim, in Germany. I think there is some background picture missing, but never mind. We can see a site map of the area in this graph. It is a mainly new built residential area that is supplied by this system. The yearly heat demand is in the range of 4,100 megawatt hours a year, so the system is much smaller than the one we have seen before. In total, there are 7,300 square meters of solar collectors installed in Kreisheim. We have the seasonal storage. The borehole storage is located, in the center of the map that we can see here. It has a ground volume of about 38,000 cubic meters of ground volume. In addition to this borehole storage, we have two water tanks as buffer storages, so one with 100 cubic meter and a second one with 480 cubic meters. Additionally, there is also a heat pump with almost 500 kilowatts installed to the system, and the calculated solar fraction for this system is 50%. If we look at the borehole storage, it consists of 80 borehole heat exchangers that have been drilled down to a depth of 55 meters. You can see a vertical section on the right-hand side and a top view on the lower left side. So the borehole heat exchangers that have been used are double U-pipe heat exchangers, and they are made from a cross-linked polyethylene called PEX. There is only an insulation layer to the top surface or towards the top surface, and it consists of about 40 centimeters of foam glass gravel. If we look at the top view on the lower left side, we can see a circular surface. So the entire storage volume forms a cylinder. And the dots that you can see on this graph, they represent the location of the borehole heat exchanger. So we have a rectangular pattern for the borehole, for the installation of the boreholes. And from the hydraulic connection, always two borehole heat exchangers are connected in series, where the first, or during the charging process, the first borehole heat exchanger that is connected is located somewhere in the center of the storage volume, and the second is located in the surroundings. Here you can see some pictures from the construction phase. On the upper left side, you can see this top circle in the center, the concrete manifold shaft and the drilling rig. On the lower left side, you can see the drilling rig during the installation of one of the borehole heat exchangers. The upper right side shows the installation of the insulation layer. So it was a bulk material, foam glass gravel that was delivered to the site in big bags. And on the lower left side, you can see the finalization of this cover construction just before it was covered with a soil layer. Here again, we can see the monthly heat balances for this storage. The red bars show the charging heat amounts for the storage, and the blue bars show the discharging of the storage. If we compare this figure with the one we have seen before, we can see on both sides, so on the charging and on the discharging side, the clearly seasonal operation. So there, if we look at the discharging side, we can hardly see any, or we can see no discharging in the summer period. This is due to the fact that the short-term effects in this case are covered by one of the additional buffer storages. So the borehole heat exchanger, the borehole storage is not affected by short-term effects. Here we can see the temperature development in the ground. So the lines that you can see here, they represent ground temperatures that are measured somewhere in between borehole heat exchangers or outside the storage volume. The red lines, they show temperatures at a position in the center of the storage in a depth of 30 meters. The yellow lines show temperatures just at the boundary of the storage volume, also in a depth of 30 meters. The light blue lines show the temperature in the ground in a distance of about 5 meters from the boundary of the storage volume, and these dark blue or green blue lines show the ground temperature of 15 from the boundary. So at the red temperatures, we can see the increase of the temperature level in the first 3 to 4 years, up to maximum temperatures of something below 50 degrees. In the last 2 years, we can see much lower temperatures. In the red lines or in the red curves, that is mainly because the operator decided to reduce the charging temperatures from the design values of 80 degrees down to 70 degrees. And this is mainly because of some concerns regarding the lifetime of the borehole heat exchanger material. So these are concerns of the operator. If we look at the yellow line, I mentioned before, show temperatures at the boundary, and we can see after the first 3 or 4 years, there's no increase in the yearly temperature development anymore. Same we can see the light blue lines go 5 meters away from the storage volume. If we look at the lines 15 meters away from the storage volume, we can still see a slight increase, but the yearly temperature increase is reduced more and more in the last years. If you look at the values of this storage, they are represented by these bars that you can see on the diagram. On the left side, there is values coming from system simulations. So the design value for the storage efficiency, so the ratio between discharged energy and charged energy is 73%. And the colored bars, they show the corresponding values from monitoring data for the years 2012 to 2014. You can see the numbers are somewhat lower. So in 2012, around 55%, in 2013, 58%, and in 2014, even lower, some 42%. These numbers, they don't indicate that the storage itself is not working, but they are more an indication that the storage is not used by the system as it was intended. This can also be seen from this second number that can be seen on the diagram, the number of storage cycles. If you compare the design value 0.65 with the values from the monitoring data, they are for 2012 and 2013. We are around 0.3, and in 2014 even lower, 0.25. This is an indicator that only half of the energy turnover could be reached by the storage, and this is not a problem of the storage. This is more or less a way of operating the storage from the system side. So yes, the main reason, as stated before, is as you can see on the bullet points below, that the storage is not utilized as much as intended. The temperature level inside the storage volume is, in the last 2 years at least, is lower as designed. This has been discussed before, and mainly because of the reduced charging temperature. This is a decision of the operator. There are some more smaller reasons, like the heat pump is smaller than designed, the buffer tank is smaller, and so on. So in the end, less heat has been charged into the storage, and for this reason also less heat could be discharged from the storage. So I will skip that one because of time reasons. So to come to the summary, seasonal heat storage allows for high shares of renewable energies in district heating systems. So in the presented examples, we have solar shares of 40 to 50%. A high storage efficiency, as for example be proved by the data that has been shown for the system in Dronninglund. However, we see, especially in the second plant, in the Bohol system in Greisheim, that the efficiency of a seasonal heat storage is strongly depending on the system integration in terms of temperature levels that are necessary for the system and can be delivered to the system, and also power rates, for example, and also from the utilization of the storage by the system. So this was my presentation. Thank you for your attention, and I will be happy to answer any questions later on.
Okay, Thomas, thank you very much. I think it was very interesting. I mean, seasonal store feel, look like a weird animal, I would say, to many people, even in the energy sector. So it's very interesting to look at real performance data, especially about efficiency and about the temperatures that can be reached really during summer. So thanks again, and just since many new participants joined the webinar, I just remind you once again that there will be a Q&A session after all the presentation, and you have in your webinar tool a Q&A window where to post your question. Just please address a specific speaker if possible. So let's move to the second presentation. Now we go to Austria to see some real operating examples of solar district heating plants, and I would say also in a distributed way, and this means from a technical point of view slightly different from the central plants that we will see later in the last presentation in Denmark. So our second speaker is Robert Zoll. He is the head of project development at Austrian turnkey system supplier for large-scale solar heating and cooling plants, Solid. So Robert, the floor is yours.
Yes, hello, welcome everybody. Thank you very much for your introduction, Ricardo. Yes, I'm quite happy to have the chance today to give you an overview about our activities and in general the activities in the field of solar district heating in Austria. And I would like to start, first of all, with a short introduction of Solid. I would like to tell you some words about Solid. Then I will move on telling you and showing you the first solar district heating plants in Austria, which has been installed in the early 90s already. Then after that, I will move on with presenting you our large-scale solar district heating plants in Graz. Yes, and last but not least, I think it's really worth to look also in the future a little bit, but also in the near future, because I'm really convinced that solar district heating has an enormous potential, especially in big scale dimensions, like we already have in Denmark and like Thomas Schmidt already showed in Dronninglund. So Solid is planning on installing large-scale solar thermal plants, and we have our headquarters in Graz. We have been established in 1992, and we're quite international. We have offices in Germany, United States, Singapore. We have a lot of partners in many countries. Yeah, and we're doing not only district heating, solar district heating, we also provide solar thermal plants for industrial process heat and for solar heating and cooling. Yeah, our USP is on the one hand that we have the know-how in large-scale solar thermal plants, means for us bigger than 1,000 square meter collector field. And on the other hand, Solid is also a full service provider. That means we're doing everything from the first contact from the client until maintenance and operations. Yeah, so let's start with the first solar district heating plants we have installed in the 90s. The story of solar district heating in Austria, let's say, started especially in the rural areas of Austria in the early 90s with the combination of biomass and solar. In Austria, we have a quite huge amount of biomass plants, and yeah, at these times, a lot of operators of these biomass district heating grids realized the benefits of solar, let's say, and so we installed the first plant in 1994 in Deutsch Schanschendorf, which is a small village with 600 inhabitants in the east of Austria, with 325 square meter collectors, a 40 cubic meter hot water tank, and 350 kilowatt biomass boiler. Yeah, by the way, the guy you see on the roof on the left side is my boss, the CEO of Solid, Christian Holter. So it's quite a long time ago, I would say. Then we will move on with a collector field or a solar thermal plant in 1995 in the eastern of Austria. It's 450 square meter. The next plant we installed in 96 in Urbersdorf, also a small village with 360 square meters. And all these plants are in combination with biomass. So in 1997, the Eideswald project was definitively for us the highlight, as it was the first plant in Austria over 1,200 square meters, and the collector area was installed on the biomass storage building. And yeah, in general, you can say that we could reach a solar fraction of 90% in summertime of the summer demand, and the surplus heat additional could be used for drying the wood chips in this building, which was quite useful, I would say. And the success story continues because in the years after that, the demand of the district heating increases and increases. And then in 2012, the client ordered another 1,200 square meter to cover the summer demand again. Okay, it was the introduction of some smaller solar district heating plants, let's say, in the rural areas, and now we are coming to these distributed solar district heating plants in Graz. The first solar feeding plant in Graz was installed in 2002 with a collector area of 1,407 square meters, and this was also a kind of pilot project for solar thermal for district heating. And yes, I think it was a strong commitment of the city of Graz to renewable energies in general. So the hydraulic, I don't want to go very deep in that, maybe for the next project, because the hydraulic is quite simple in that project. We do not have any storage tank. We are just feeding in directly into the district heating grid. And yeah, we have in summer, the district heating grid has return temperatures of approximately 60 degrees. And we have reached, or we are still reaching, approximately 500 megawatt hours a year solar yield, which is quite good, I would say, considering that 10 years ago we didn't have any advanced flat plate collectors, so we have really installed standard collectors without any Teflon foil or without any additional glass between the absorber and the glass of the collector. We also had no major failures in 14 years operation, and we do not have any stagnation yet. Okay, sorry. The second plant I would like to show you in Graz is located at the premises of the water utility with a collector area of almost 4,000 square meters. Here the hydraulics are a little bit more complex, as the solar energy is not only feed into the grid, but the solar energy also supplies heat to the buildings of the water utility. And we have also installed an electrical heat pump. And furthermore, a storage tank of 60 cubic meter is also installed. So you see an aerial view there of the premises. You have the ground-mounted collector field. You have the red pipe, which is representing the district heating grid, district heating pipe, and the building, which is marked with the orange circle, is the building where all the solar equipment is installed. And the tank is also placed in a lower position inside a fountain house, which is quite curious a little bit, which you can see maybe next to this technical building, also marked with this orange circle. And these other buildings, the surrounding buildings you can see here, are also supported with solar heat in wintertime and in the shoulder season. So some words to the hydraulic. This is a very simple hydraulic. And we have the collector field, and then you have first the heat exchanger, which is feeding into the district heating grid. You have the heat exchanger, which is transferring the heat to the storage tank. And from the storage tank, the heat goes to the buildings in winter for heating time. And additionally, as I already told you, we have a heat pump. This was financed with an R&D project with the goal to use the low temperatures in winter time and in the shoulder season and in the evenings to increase the solar yield in total. So the experience of this heat pump was that we have a quite good COP of at average of 4, but the problem is that we have quite less operation hours, quite a less amount of operation hours, and of course this doesn't make it very economic. Yes, in addition to store the solar energy into the tank also has, let's say, also make a load management. And so by cutting the peaks, the tank also enables to decrease the connected district heating load. Yes, we have quite a high solar heat for this project because of the combination of room heating and solar district heating. And yeah, that's it. And now we are coming to the last project in Graz. It's actually the biggest solar thermal plant in Austria. And we have started with the installation of 5,000 square meters on the roofs of the waste treatment facility in Graz in 2007. And then from 2014 till 2016, further 2,750 square meter collector area were installed on the premises nearby the district heating plant of Graz, which you can see at the second picture on the right. It's also a very simple hydraulic, let's say in general, but the special feature here in this project is that the system extension, the 2,750 square meter, have been realized with 6 different collector types from 5 different, quite well-known collector producers, I would say. And these collectors are now compared in a large-scale field test under a scientific survey. yes, to the solar yield for this plant of the Fernheitswerk. Sorry. I don't want to compare now, as these here you can see monthly solar yields of 4 different collector types, let's say. I don't want to go in detail now regarding the differences between the collector types, because we had some influencing parameters this year, like shadowing, like some measurement faults. Yes, so therefore I want to go into the details, but we also have some changed some foils. But I think the really interesting and impressive thing is that we already can say we can reach now 470 to 500 kilowatt hours per square meter a year, which is compared now to the first plant that we have in Graz, with almost the same conditions, at least regarding the return temperatures. So there is really a high increase of solar yield comparing UBC Arena in 2002 and 13 years later, 2015. Okay, now I'm coming already. Sorry, I'm coming already to the end, and would like to make an outlook of solar district heating. And we see the potential in big solar plants. And maybe as an introduction of this chart, you can see the monthly heating demand of the district heating circuit Graz from May to September. And the green part represents the renewable projects, which is covered by renewable projects, existing solar plants, and also waste heat especially. And you can see there is not that much space left. And so what is the solution? For us, the clear solution is we need to use long-time storage, of course, and also in bigger dimensions like we have it in Denmark. So therefore, I prepared one slide where I could, of course, tell more than 15 or 20 minutes regarding just this project. But I would like to tell you this project because we said, okay, it is economic, it is technically feasible. We made a feasibility study, quite detailed feasibility study, together with some partners, together with the energy utility of Syria, with the local energy agency of Graz. And the economically most feasible concept has shown following figures. So the collector area of 450,000 square meters, there's a seasonal storage of 1.8 million cubic meter. We will include some absorption heat pumps with a total size of 100 megawatts. Yes, and the nice thing is that we really can then cover more than 20% of the total district heating demand. Now, with these 3 plants I've showed you before, we can reach roughly 1%. The heat generation cost is also quite interesting, I would say. Here we calculated around 35 euro per megawatt hour. So the summary, in the last 20 years, I think we have shown with a lot of projects that it's not innovative anymore, solar district heating. I think it's a proven technology already. Then I showed you before that the collector efficiency has increased, and especially also the quality of the flat plate collectors has increased. And yeah, I'm convinced that big solar solutions like we have it now in Denmark is the future, and it's not the future in 5 years or 3 years. It's now, let's say, in combination with seasonal storage. And last but not least, what I would like to say, we see more and more that, of course, the district heating network will not be energy just from one central fossil-fired heating plant. It will be a mix of a lot of energy sources like industrial waste heat, like biomass heating plants, CHP, and so on. And therefore, I think in this concept, I think solar district heating plays really a crucial part for the future energy mix of renewables. And I would like to sum up with one slide, which I saw already twice from Paul Potts, the managing director of Euro Heating and Power. he was very proud in these two conferences when he made his presentation that heating and cooling is already on the agenda in the EU, in the European energy transition, and I think that is also quite good for solar. That was from my side. Thank you very much for your attention.
Thank you very much, Robert. I think it was really interesting to see the change, let's say, that you were able to do in Austria, and especially, of course, I was not surprised, but I was very happy to see the increase in the size of the plant and also the increase you show from a technical point of view in the solar yield, because actually these two items can really increase also the economic by such solution. And from this point of view, I think that the project of Big Solar Graz could be really I would say not the end point, but maybe the starting point. And I also would like to thank you for the very inspiring end of your presentation. I think it is very important to highlight that really solar district heating is at the moment a niche market, but it could really play, as you said, a key role in the energy transition at local level. So I think this is very important to communicate, not only to the solar thermal sector, of course, we know it very well, but to local and regional authorities. So I think that is a key point for such technology. Okay, so thanks again. And we move now to the third and last speaker. We now move to Denmark. Denmark is the, by far, I would say, so far, the best country for solar district heating. They have several operating plants and many of them also in the pipeline. And usually these are centralized plants in their district heating grids. And so we would like to see now an example of how these plants are monitoring and how the simulation of these large solar district heating fields is operating. So I now give the floor to Jan Erik Nielsen. He's a project manager at the Danish consultancy Plan Energy, and he also manages the Solar Key Mark network and the Global Solar Certification Network. So Jan Erik, the floor is yours.
Thank you very much, Ricardo, and hello to everybody. So yes, in Denmark we have been quite successful in solar district heating. In round figures, I think we have around 100 plants and altogether more than 1 million square meters of these systems. So, but today I will be a bit more specific on the subject. So I will talk about how we can also check if these systems are performing as they should or as expected. So I will present a quasi-dynamic model for simulation of these fields, and this could lead to a method how to control the systems online. Oops. So the basic equation for this quasi-dynamic model is well known, I think, and quite simple. So you see it here. So it's the capacity and the change in temperature per time, which equals what comes in and what goes out of the collector field. So we have the solar radiation and the heat loss and the output of the collector field on the right side. So there's a solution to this. It looks maybe strange, but it's not so complicated, so it can be incorporated in the online control system if you want. So, and here is the equation for the collector loop mean temperature at the end of a time step. And this is what we are checking on, one of the things. So we can calculate the outlet temperature and the calculated output during this time step. So this is our model, and we tried this out on a system in southern part of Denmark, which is in the cluster district heating, you see the field here. We have 32 rows with 11 modules in each row, and total area is 5,600 square meters. The collector is a Solar collector, and we use the data for a new solar key mark test. You see the data here. So this is what goes into the model, together, of course, with the fluid content and so on. And we chose a period with really Danish summer weather. So here you see this is clouds on a blue sky, so up and down in solar radiation all the time, and even with some gray days too. So very dynamic period. This is then on an hourly basis, the calculated outlet temperature compared with the measured. So you see this is quite good. What you should compare is the temperatures in the operation period, because you will see that there's a big difference between the red line and the blue line in the night. And this is because the sensor is placed in a well-insulated pipe, taking the measurements, and we calculate the temperature in the solar collector field. But they go together in the morning when it starts. And then looking at the hourly calculated output and compare this with the measured one, you see also an extremely good agreement. Just to show you one day, this is one day of solar radiation. You see how much it varies all the time. And this is then the same day with the T out measured and calculated. And same for Q out. So even though that we have a very up and down in the solar radiation, we calculate quite good what's coming out of the system, even though we use hourly values. This is then the measured compared to the calculated, so this should be a 45-degree line, so they should, if everything was ideal, be on this center line, but you see they are almost on the center line, so and all of them, except one I think, is within this plus minus 10% on an hourly basis, and this is also quite good. Of course, looking at the daily values, you have even better agreement, and you see in the end the average. I think the whole period we get less than 1% in deviation. So this is maybe better than expected. So we are quite happy. Then this is what you could use it for. So you can put in some warning criteria. I'll try to use this arrow. So, and every time there is a deviation more than something between the measured and calculated value, you can put a warning or an error. So this is to warn the operator that he should maybe check. And here I put some quite narrow or strict requirements just to see that some warnings are coming. And these are all always in the morning, so the morning is the most difficult period for the model to fix. So this is on the Q, and you can do the same on the outlet temperature, and you get warnings and a single error also here. So this can then be used by the operator to see online if the system is always working as it should, and so you can very fast take corrective actions if necessary. So this was it actually, but I can tell you that you can see 50 systems in Denmark, and they have a lot of measurement data and also data on economy and so. So if you click into this website, which is now also available in English, you can see a lot of details on the Danish systems and also measurements. So you can enjoy that, and this is for my part. Thank you.
Thank you, Jan Erik. Again, I think this is really a key issue for solar district heating, especially, I would say, for newcomer countries. So I have, of course, a direct experience from Italy, but we really need good and maybe long-term performance data for, of course, showing our potential developers, which could be utilities or municipalities, that these plants are working and that they are reliable, and also that they perform quite well in comparison, as you showed, with the simulation, with the design values, let's say. And honestly, I must say that in Italy we just had one example of solar district heating plant, which is, by the way, very small in comparison, of course, with the Danish ones and also with the Austrian ones. But I must admit that from the first year of performance, I saw very encouraging and good results. So I think that this kind of data, maybe at this technical level or a bit less if we are interacting with different actors, but we have really to show this kind of data. Okay, thanks again. So now I think I will open the Q&A session. So I ask all the presenters to be ready for questions. Let's say, I think actually the first question is to Fernando. So if the presentations will be available afterwards, I think yes, maybe I can answer, and Fernando can correct me if I'm wrong. So the presentation will be available on the solarthermalworld.org web portal together with the recording of the webinar. Okay?
Indeed. Thank you.
Okay. Thank you. Okay, so just let me check. Okay, there's a question for Thomas Schmidt. If you can compare the costs of tank types, so of seasonal heat storage types.
Yes, of course, this is possible. I don't know if is it possible to go back to the presentation? Actually, in the last slide, there is some cost information. Maybe we can have a look on them.
Yes, one moment, please.
So what we will hopefully assume that there is a strong dependency of the cost of these kind of storages. The very last slide, so one after my final slide, this one exactly. So what you can see here is a strong decrease of cost with size of the storage devices. So please also consider the logarithmic scale on the x-axis. So if it comes to storage volumes of, let's say, more than 10,000 cubic meters, then costs are really much lower than for smaller devices. And what we can also see, or what you can also see from these slides, there are the different colors of the different examples here. They also represent different types of seasonal storages. And in general, we of course see that the tank storages are more in the upper area of this range, defined by the two orange lines, whereas the underground storages like aquifer and borehole storages are located more at the bottom. It is, however, very difficult, as might be, maybe could be seen already during my presentation, to compare storages and storage concepts, because the influence and the connection to the connected system is really crucial. But even if you try to compare storage concepts in a similar kind of application, you have to consider that that there are also differences in terms of thermodynamic capabilities between the storage concepts. So, for example, with a water volume, you can reach much higher temperatures in the storage volume. You can more easily create large power rates for charging and discharging and so on. And this can, of course, create many advantages on the system side. On the other hand, the underground storages can be much cheaper. They are more limited regarding temperature levels and power rates, but depending on your connected system, they can still be the most economic solution. Maybe there is a need for additional supporting components, like, for example, buffer tanks or heat pumps, but if you optimize on a system level, they can still be advantages.
Okay, thank you. Maybe, Thomas, I will use this opportunity also to ask one more question to you. So about the peat thermal energy storage, could you give some details about the plastic foil between water and ground? So if you know about the thickness and which is the material used.
Yeah, it's normally so in the large storages that have been recently built or are still built in Denmark. They more or less all use the same kind of foil, and it's a high density polyethylene with a thickness of something around 2 millimeters. I don't know exactly. And the main limitation of this foil actually comes from the maximum temperature and from the lifetime of the material with respect to the temperature history, so to speak. So all plastics show a strong degradation depending on the temperatures they see in their lifetime, and especially the very high temperatures that are close to the maximum temperatures reduce the lifetime very much. So in the Danish projects, the temperatures we have seen in Dronninglund, they go up to 85, 90 degrees. And with these maximum temperatures during the summer period, of course in the heating season or in the winter season we have lower temperatures, but with this development during the year, the storages are calculated to a lifetime of something between 15 and 20 years.
Okay, thank you. I would go now to Robert, maybe for a couple of questions. So you showed that there has been an increase in yield, in the average yield of solar district heating systems in Austria from 330 to almost 500 in, let's say, Can you explain briefly about which are the main factors thanks to which this increase has taken place?
Yes, it's of course the main part is of course the advanced flat plate collectors, including either a Teflon foil or a glass. Of course, this is it, and then of course the whole quality of the collector has increased. The quality of the foil, the quality of the glass, the whole assembly of the collector itself, the quality was getting better and better. So yeah, that's it more or less. But of course, in the first view, it's the same collector. But yeah, there are these small differences why we have this increase. Yeah.
Not a matter of grid temperatures, so of operating temperatures for the...
Not really. Of course. Between these between UBC Arena, Waterworks, and Fernheitswerk. Of course, in Waterworks you have more solar yield because we have a small portion of supporting heat to the buildings. Therefore, we have at the average a little bit lower to return temperatures. But in general, the district heating grid has the same return temperatures like for 10, 12, 13 years. And maybe it's also maybe one additional parameter could also be that Fairtech is that much better, because here we are measuring quite next to the collectors, and maybe in the UBC Arena there are also some percentage losses between the collector and the heat meter.
Okay. And just connected to this question, what is the feeding, so the flow and return temperatures in the grid in Graz?
Yeah, depending, of course, of if it is summertime or winter time, we have different average flow temperatures. But in summer, of course, it can go up until 100 degrees also, and in winter time also 60, 70 degrees flow, and the return temperatures are 60 degrees in summertime, and let's say 75 to 80 degrees in winter time. Or no, it's almost a little bit higher it's almost the same in summer and winter and Christmas. Yeah.
Okay, thanks. And so now I go but I go for the first time to Jan-Erik for a couple of questions also. The first question is about the alarm you were mentioning. So how does the alarm work? Just after an immediate comparison of calculated and measured values, or do you first integrate this deviation over time and then there is this alarm?
Yes, so the idea is to have an immediate alarm. So right now we are working on an hourly basis, but I guess we can go down in time step also. But right now it's possible, or will be possible, because we are implementing this system at the moment. It will be possible to, after 1 hour, to have this alarm. And I see there's another question about the solar irradiation values more than 1200 watt per square meter, but this is because it's minute values, and there are some reflections in the skies, in the clouds, from the clouds.
Okay, so higher than the usual maximum value, let's say.
Yeah, so if you go to an hourly average, you will not have values more than 1200.
Okay, just a second quick question. What do you consider as average temperature? Is it just the average of inlet and outlet temperatures in the solar field?
Okay. Yes.
Okay, so there is a question. Again, I go back to Thomas Schmidt about the financing, the sources of financing that enabled the implementation of the cryoscience system. So how was it financed?
The cryoscience system was funded by the state of Germany and also by the state of Baden-Württemberg. So Baden-Württemberg mainly funded part of the solar collector areas, and from the federal government mainly the storage part was funded.
Okay. Do you see this as really a pilot project, or just because of this big funding, or it has also some potential of replication potential, let's say?
I see there is a replication potential. We have, maybe we have to go back a bit. So in Germany there was a long-term research program for the strategic development of these seasonal storage concepts, and that started somewhere beginning of the 1990s and ended somewhere 2005, 2010. And within that period, there were a number of specific research programs with a focus of seasonal solar thermal energy storage, and with a focus or with a target range for the solar contribution on a system level of about 50%. So this was the framework for in total 11 demonstration projects that have been realized between 1996 and 2005, 2006 in Germany. And within these 11 demonstration projects, all 4 of the in the beginning mentioned storage concepts have been realized at least once. So it was more a research and demonstration project to develop the technology and to show that it's from the to show the technical feasibility. But of course, at this development stage, there was no economic feasibility. Meanwhile, if we for example look to Denmark, the large solar systems, including the storage systems, they are built without any subsidies, because under the Danish boundary conditions, they are the most economic solutions. We don't have this situation at the moment in Germany, unfortunately, but I see still a large potential.
Okay. Maybe one more question to you again. What is the principle of using heat pumps, so to increase the temperature level of the storage before going to the consumers? And then what is also the ratio of the electricity used for this heat pump with respect to the total energy delivered? So if it is a major point here.
Yes. So the heat pumps, they offer a number of advantages as well for the storage component and also on the system level. So in the first 2 or 3 projects that have been realized in this German research context, they have been realized without heat pumps, and it could be seen that the efficiency or the usability of the storages was much lower than expected. And one of the main reasons was that the return temperature of the district heating network that is connected or that is supplied was much larger than expected. And if you don't have a heat pump in the system, then the return temperature from the district heating network defines the lowest temperature level in your system, and by this also the lowest temperature for the discharging of the storage. And in one of those projects, for example, there was the district heating network was designed for temperatures of 70 supply and 40 return, and in reality the return temperatures were in the order of 55 degrees. So and without the heat pump, you directly lose 15 Kelvin of temperature difference in your quite expensive storage component. So it's for the storage component, it means with a heat pump you can at first extend the usable temperature difference from the upper limit is normally given by for some water volumes. They are non-pressurized, so we end up with some maximum temperatures of, let's say, about 95 degrees. And the lower limit is given without a heat pump by the return temperature of the district heating network. Let's say if you have a good network and around 40, maybe 45 degrees, but with a heat pump, as you can see in the Dronninglund data, you can go down to 10 degrees. That means in the end almost double the heat capacity with the same volume. And the second advantage is that you become kind of independent from any variations during longer operation periods from the return temperatures of the network.
Okay.
Coming to the second part of the question, the efficiency of the heat pumps. So at the moment, more or less all the heat pumps are special heat pumps that have been realized especially for the different applications. So it's no products that are delivered by standard from companies. but because of the high source temperatures and the low lifts, they in general they reach yearly COP values of something between 4 and 5.
Okay. Thanks again. I maybe go back to Robert for a couple of slides. One is about the UPC arena. So there are two questions about this plant. What is the feed-in temperature from the panels, from the solar panels, and is there any thermal production also in winter time?
Depending on the day, but the maximum feed-in temperature in summer, let's say, is 100 degrees, something like that. And of course, in wintertime, the solar heat is very neglectable. So in the summer half year, let's say, we have more than 90% of the whole total solar heat. So we have winter production, but yeah, it's not that much.
Okay. And the second question is a very tough one. So how big are the chances for this big Solar Graz to be implemented, and how do you see also the timeline for that? So when the decision should be taken from the authorities?
Yeah, that's not a question what I'm asked the first time. So yeah, I would like to know it also. The problem is it's not a problem. Now the activities are ongoing. A lot of activities regarding securing the land are done at the moment. And I know the contract now between the VKR, Akon Sanmark, is between Energie of Graz and Energie Steiermark. A pre-contract is also done. And yeah, I don't know. I cannot answer the question when there is a decision to really make it, but I'm quite sure that we will realize it. The only question is when.
Okay.
Sorry for not giving a better answer, but yeah, it's not very easy.
Also helpful to hear your general attitude towards that, let's say. Okay, yeah. Thanks. So maybe again to Jan-Erik, about your monitoring control software. Is it currently used by all planners in Denmark, and do you think it can be also used outside Denmark for similar plants?
So, right now we are implementing this in Dugum cluster, so this is the first plant. So I hope and I count that it will be used many more places. And for sure, it's also usable outside Denmark, yes.
Okay.
But it's not it's not a final commercial product yet. It's under development.
Okay, maybe I ask you about also a different question, which is addressing all speakers, which is more maybe a policy and economic question. So what would be necessary to change in the policy framework to have a solar district heating economically interesting, let's say, at massive level?
So I think in Denmark it's successful for several reasons. First, it's because we have a long tradition for district heating, also in towns outside the big cities. Next, we have a tax on gas and oil and coal and so on, so it's quite expensive, the alternatives to solar. And for some reasons, it's also the district heating companies are normally user-owned and small companies, and they're quite open to this kind of projects. So this is some of the reasons why it's successful in Denmark, at least.
Okay.
Yeah.
And Thomas, for Germany, if you could say just one piece of advice, let's say, for changing the policy framework to make SDH more interesting?
Yeah, well, it's kind of a difficult question, of course, but I see at the moment we have quite good conditions regarding support of solar district heating systems. But in my personal opinion, in the end, if you want to go towards a successful energy transition, then we need to switch a little bit more towards the direction that Denmark went already years ago. That means we have to think what do we want to have and what don't we want to have. And one way is to give support to what you want to have, but maybe the more successful way is to get a kind of a penalty or taxes on things you don't want to have. So maybe that would be an alternative.
Okay. And an opinion by Robert for Austria?
Yes. In Austria we have already quite good conditions, especially for subsidies, for example. But of course, there's one thing, and this is really my personal opinion. If you would pay taxes, a lot of more taxes on conventional energy sources, of course, this would make it easier. And the second thing is that we recognize that already in our big Solar Graz project, that maybe also the policy can do something in regarding getting land easier, for at least for solar thermal plants, because this is maybe really a point where we need place. We know we need not that much place in comparison, for example, for biomass or something like that, but we need place, and for this the framework conditions should be made that it's going a little bit easier.
Okay, maybe Robert, I ask you an additional question. So if it is possible to better explain what is the funding scheme for the big Graz plant, so who will basically fund this plant? How is the financing made?
Yes. No, there is no funding scheme at the moment. There is no official funding scheme, because the fundings actually are like that we have a maximum of 10,000 square meter, and out of these 10,000 square meter you get, let's say, 40%, and that's in total not that much when you see 200 million euros. But we had all stakeholders had a lot of discussions with the Austrian Klimafonds and with these responsible person, and we have at least a very good response, and they say, okay, we can subsidize. We want to subsidize it, but yeah, there is nothing fixed at the moment.
Okay, thanks.
No,
maybe I go back to Thomas, because there is an additional technical question about the heat pump COP. So the question is, if the COP is around 5, isn't it cheaper to produce heat from the heat pump and just, let's say, get rid of solar thermal? So how is your opinion about that?
No, the high COPs are only possible because of the high source temperatures. So the source side of the heat pump is connected to the seasonal storages, and without the solar system, this heat source would not be available, and then the COP would also be much lower, because then the standard alternative heat sources would be ambient air or ground source, but those have much lower temperatures.
Okay, and just one additional question regarding the borehole thermal energy storage efficiency in Kreisheim. How do you explain that there is a larger share of direct solar usage?
There's mainly one reason. I mentioned the total heat load in the network that was estimated during the conceptual or the design phase at the very beginning of the project, and this was estimated at that time based on some first plans for this new residential area to about 4,100 megawatt hours a year. and so this, in reality, this heat load was increasing the last years and followed more or less the realization of the residential area. But the last 2 or 3 years, the real heat load was about 20% higher than the estimated heat load during design. That means also the summer heat load is higher and is covered by the solar heat, and this extra solar heat is then not available anymore to be charged in the seasonal storage.
Okay.
So that's the main reason.
Mm-hmm. I have now an additional question. Maybe we start from Robert, but I also would like to ask Jan Erik's opinion about the flow rate in the solar collectors, in the solar fields. So would you, let's say, suggest a fixed or variable mass flow rate to improve the collected energy in such large plants? Maybe Robert can start.
Yes, so we are already working since so many years with variable flow rates.
Yes,
we have pumps, frequency controlled pumps, so yeah, that's standard.
So same in Denmark, and it's actually quite important to have a good control of the pump and the flow rate. And we do this, we control it on the solar radiation, and so we have a fast response.
Okay. Maybe we can just do a last round with the same question. So I will ask the same question to all 3 speakers because it's a question about perspective. I think we talk about 100%, let's say, renewable district heating system also. So is it possible to go for a very high share, let's say, renewable district heating system combining just solar thermal and heat pump? If yes, how do you see this, for instance, the relative size or the relative production from solar thermal and heat pump, or do we always need a more conventional, let's say, heat production? So maybe we start from Thomas.
Yes, I mean, there are a number of projects proving that it's possible to have a high share of solar heat in district heating systems. So between, let's say, 40 and 60%, even some single examples with around 70% are available. It is, of course, from the economic point of view, the last some percent are much more expensive than the first some percentage. So this is maybe kind of an economical optimization. For these higher shares, in my personal opinion, a heat pump plays an important role to reduce the effort on the solar side or on the storage side. So for the economic optimization, I see an important role of the heat pump. I don't think that 100% or 90 or 100% solution only based on solar and heat pump is, from the economical point of view, really recommendable. So I still see some kind of backup peak heat source that could come from somewhere else.
Okay, so mainly from economic point of view rather than from the feasibility from an energy point of view, let's say. Okay, thanks. Robert, would you like to add something on that?
Yes, I would say we made also other feasibilities regarding this big solar issue, and of course, when we are speaking about district heating now and solar, including absorption heat pumps, we think that it is economical possible to reach at least 50%. In a city like Graz or something like that, when you have really lower return temperatures, of course. In Graz we have quite high return temperatures, so 50% is really also possible from an economic point of view, I would say. And then, if we're talking about renewables in general, I would say combining it, as we have it also in Graz now, to use waste heat and to have biomass and so on, I would say the future energy mix, and 80% of renewables, I would say, is really possible if you use district heating as a core distribution grid.
Yeah, and so also let's say that the future district heating grids can be also designed to meet, let's say, the requirements from the renewables. Okay.
Exactly.
Jan-Erik, would you like to add something?
Well, I can say that we have, or in Canada, there's already a 100% solar fraction system in Drake Landing, and this is due to very low temperatures in the district heating network. So very good heat distribution systems in the houses. So it's possible to go in for high solar fractions, but of course you have to see also on the economy. But if you have a good district heating network with very low temperatures, you can go higher than if your temperatures are high. And it's very easy to have 100% renewable district heating systems if you also use biomass. So.
Okay.
Hello. Yeah.
Thanks again. So we now came to the end of the webinar. I'm sorry for not being able, let's say, to address all questions, but there were really many of them. So thank you. Let me thank again the speakers for contributing to this webinar, and of course European Copper Institute for hosting the webinar. And I thank you all for being with us. And I just remind you that solarthermalworld.org, the portal which also did a very good promotion for this webinar, will make the recording available in about 24 hours. So please just check the website solarthermalworld.org. And thank you all again for listening and for being with us. Thank you again and goodbye.